Hello, my name is Julia, and I'm a PhD student at Cornell. In this presentation, I'll be talking about partitioning Oracle attacks, which is joint work with Paul Grubbs and Tom Ristenpart. At a high level, this talk will be about why certain kinds of authenticated encryption can be dangerous and lead to vulnerabilities. I'll start by giving an overview of authenticated encryption in general, and for simplicity, I'll ignore associated data here. So here in this setting, we have a client and a server who both share a secret key. The client chooses a nonce and a plaintext message, and then encrypts this using its secret key to produce its ciphertext. The client then sends its nonce and ciphertext to the server, who can decrypt it using its secret key to recover the plaintext message. And of course, we expect that an attacker who sees the ciphertext won't be able to decrypt without having access to the secret key. There are many popular AEAD schemes out there, such as AES-GCM, XALSA20, Poly 1305, and many others. They are popular for good reason. They're efficient, they're standardized, and they're widely supported by many libraries. And they also guarantee many security properties, such as confidentiality and integrity, as well as being proven chosen ciphertext attack secure. However, there's one security property that these AEAD schemes do not target, and that's robustness, which is also called committing AEAD. Now, in a non-committing AEAD scheme, you can compute a ciphertext that can successfully decrypt under two different keys. So now in our setting, the client has two keys, and the server still has just one. And while the client knows that one of its keys is being used by the server, it might not know exactly which one, but that doesn't matter here. The client can simply send the ciphertext that can decrypt under two keys, and the server, as expected, will still be able to decrypt it. So notice what this means. There's no guarantee that the sender actually knows the exact key the recipient will use to decrypt. And for the most part, robustness or key commitment hasn't been considered an essential security goal, except in moderation settings. So then, are vulnerabilities stemming from non-committing AEAD just a niche issue? The short answer here is no. To understand why, I'll give you a quick, high-level overview of a partitioning Oracle attack and how it can be used to break confidentiality by recovering a password. So in this setting, we have a server with an associated password. The server accepts encrypted queries, which it then decrypts using a password-based non-committing AEAD scheme, so something like AES-GCM. Now the attacker wants to recover the server's password. To help with this, we assume that the attacker has access to a password dictionary, which they could have gotten from linked password data. We also assume that the server's password is a member of the password dictionary, although of course the attacker doesn't know which one it is. So the attacker could make a single query for each password in the dictionary in what's known as a traditional brute force dictionary attack. If the server responds with some decryption error, the attacker knows it's not the right password. But if the server responds with success, then the attacker knows they have the right password. But password dictionaries can be large, and this technique could be prohibitively expensive, especially if the number of queries the attacker can make is bounded. So instead, the attacker can do this. The attacker can split the password dictionary into two sets, and then compute a nonce and a ciphertext such that it can decrypt under every password in this first set, but under no passwords in the second set. We call this a splitting ciphertext. We say it has an associated value of k equal to 4 because it can decrypt under 4 different passwords. So next, the attacker queries the ciphertext to the server, which then attempts to decrypt the ciphertext. The server's password is not in this first set, so of course decryption will fail. Now the server responds with a decryption error, which tells the attacker that the server's password couldn't have been in this first set of passwords. The attacker can now simply eliminate this set altogether and reduce its dictionary in half. Comparing these attacks more directly with a brute force dictionary attack, the attacker can only eliminate one password with each query, meaning this will require big O in size of the dictionary number of queries to learn the password. However, for a partitioning Oracle attack, with each query, the attacker can eliminate half of the password dictionary every time. The attacker can continue with this binary search-like technique until they recover the target password. This means only big O log in the size of the password dictionary number of queries is needed to learn the password. Notice that this is an exponential speedup over a brute force dictionary attack. Of course, password dictionaries can be extremely large, and it might not be practical to make such a query. But if we consider a more practical value, such as k equals 5,000, we see that for each query, the attacker can still eliminate 5,000 passwords every time until the attacker reaches the correct set of 5,000 passwords, after which the attacker can proceed with the binary search-like technique. This case still offers a good speed up over brute force. Now, partitioning oracle attacks really rely on two things. The first is building splitting ciphertexts that can decrypt under k different keys. And the second is gaining access to partitioning oracle. We'll start with this first goal, which is computing what we call key multi-collision attacks. GLR first showed an attack against AES-GCM for k equals 2. We'll show how to do this attack for any value of k. To give a high-level overview of AES-GCM, it follows the encrypt then MAC paradigm. For encryption, it uses counter-mode encryption of AES, and for its MAC, it uses Ghash, which is a polynomial MAC. Our attack algorithm will take as input k different keys, and it will output a ciphertext that decrypts under all k keys. The length of the ciphertext will be k 16-byte blocks, and the algorithm will run in big O of k squared time. Now, what really enables our attack here is the fact that Ghash is a polynomial MAC. This reduces finding a ciphertext to solving a set of linear equations. I'll now go over a quick example with 3 keys here. Our input will be a nonce, an authentication tag, and the 3 keys. Our goal is to compute a ciphertext that decrypts under all 3 keys. First, we pre-compute values, which will be the coefficients of our system of equations. Our system of equations will have 3 variables, with each variable representing a ciphertext block. This means our final ciphertext will have 3 blocks. We then set up the system by computing the Ghash tag for each key in the typical way. We can then simplify this to get the resulting system of equations shown here. Notice that the left-hand coefficient matrix is a van der Waals matrix. This means we can use a more efficient technique for solving called polynomial interpolation. We implemented this algorithm using SageMath and Magma and performed timing experiments on a Linux desktop. The results are shown in the table here. Notice that we were able to make a ciphertext that decrypts under greater than 4,000 keys in less than 30 seconds. I'd also like to point out that there does exist an algorithm that does polynomial interpolation in big O of k log squared k time instead of big O of k squared time, so it's possible to create multi-collisions much faster. In addition to AES-GCM, we found that XLSA 20 poly 1305, CHA 20 poly 1305, and AES-GCM SIV were all also vulnerable to key multi-collision attacks. However, these attacks are more complex and less scalable than those for AES-GCM. Now that we've covered key multi-collision attacks, we'll move on to covering gaining access to partitioning oracle. In other words, where do partitioning oracles arise? We performed 2 case studies. The first was on Shadowsock's proxy servers. Shadowsocks is a popular internet censorship evasion tool that's widely used in China. It's also used as the core of other censorship evasion tools, such as Google Jigsaw's Outline VPN. We showed we could successfully recover a password from a Shadowsock server using a partitioning oracle attack. The second case study we did was on early implementations of the opaque asymmetric PAKE protocol. Opaque is a password authenticated key exchange protocol that was selected by the IETF CFRG for standardization. It's meant to replace existing password authentication protocols on the web. We found that many of its early implementations went against the protocol specification and used a non-committing AEAD scheme, mainly because of the ease of use of a non-committing AEAD schemes that I mentioned earlier. These left these schemes vulnerable to partitioning oracle attacks. And in addition to these case studies, we found that there were other possible partitioning oracles. These included hybrid public key encryption, Auge file encryption tool, Kerberos straps, which weren't adopted, JavaScript object signing and encryption, and potentially anonymity systems. For instance, an attacker could use partitioning oracles to learn which public key a recipient is using from a set of public keys. Ultimately, our paper is the latest in a growing body of evidence that non-committing AEAD can lead to vulnerabilities. And this tells us that we should transition to using committing AEAD as a default. But when we ask which scheme to use, this is currently difficult to answer. No scheme has been standardized. So really, this all tells us that we need a committing AEAD standard, and it should be the default choice for AEAD. To conclude, we described partitioning oracle attacks, which exploit non-committing AEAD to recover secrets. We talked about how widely used AEAD schemes are not committing, and we showed that partitioning oracle attacks can be used to recover passwords from tools and protocols used in practice. Finally, our recommendation is to design and standardize committing AEAD for deployment. If you have questions or want to learn more, I have my email on the slide, as well as a link to the full version of the paper. I'd like to thank my co-authors, as well as those who provided helpful feedback on our paper. Thank you all for your time, and I look forward to answering your questions.